Okay.
So welcome everyone who is here in person and online on Zoom. So this is the third meeting of the reading group, and today's speaker is Alexandru Cioba, and we will talk about the mean field limit of certain deep neural networks. I posted the archive link to the paper in Slack, and well, you can join the discussion either on online on Zoom or on Slack in the reading group channel.
Sure.
Thank you for joining us, and the floor is yours.
Okay. Yeah, thank you very much for having me. I'll just say something very brief about myself. I work for MediaTek Research, which is an AI research branch of Taiwanese semiconductor company MediaTek. Previously, I studied here in Cambridge and did a PhD in geometry and dynamical systems in London. So nowadays, I mostly work on topics related to what I'll be speaking about today. In particular, I thought that this paper would be quite relevant to this reading group, and it's also something that a paper that I hold quite dear, having also met one of the authors at some point during the time of my PhD. Okay, so to begin, these kinds of problems have been garnering much more popularity in recent years. The study of various scaling frameworks for deep neural networks has attracted attention due to the observation that the classical bias-variance regime of training parametric models has a very particular behavior in the case of deep neural networks, where the training dynamics actually simplifies as the number of parameters tends to infinity. And the central question is, okay, how to let the number of parameters tend to infinity. So this is why the paper is actually called a mean field limit of certain deep neural networks. Okay, so we're going to go very quickly and define the objects that we're looking at. So these are just going to be parametric functions. We'll call them y hat. They're defined from some input space, some parameter space, into some output space. Okay. So these are going to be the dimensions of the corresponding input-output vectors and parameter vectors, and we plan to do supervised learning. So, by the way, I'm going to speed through this as much as possible, but do stop me if there is anything that I should say or clarify. So we're planning to optimize some sort of loss function over IID data. So we have IID data distributed according to a probability P on X, Y in RDX R. Dual. Okay, and we're aiming to optimize some sort of loss function as an expectation over this probability distribution of y minus y hat x theta n. All right, so for the paper that they have in mind, there is a fairly general type of MLP that they consider. It's not a standard MLP, but we will we'll clarify exactly what this means. So we're going to be working with some capital L number of hidden layers. And we're going to work with the sequence of dimensions for the inputs and activations of every layer, which is the dimension of the input, DL+1, DY. These are the dimensions of the activations. Okay. And the activation functions at each layer L, they're going to be defined from DL cross capital DL to our DL+1, okay, where this is the dimension of the input. So this is what gets plugged into the activation function. This is the parameter. And this is the output, obviously. Okay, so just to kind of keep the analogy going with typical neural networks, and we're going to denote by theta L and usually some subscripts here a parameter, for example, right, IL+1. This will be the parameter corresponding to edge IL+1 in between layers L and L+1. Okay. We're going to write theta n, the one that you see in the loss function there, to be the collection, the concatenated vector of all of these parameters. Okay. Yeah. Where this is the size of layer, L. So in what follows, we're going to have NL is equal to a constant n for these values of L, and N0 is going to be equal to N L+1, and is going to be equal to 1. Okay. So the total number of parameters is going to be this sum over L equal 0 to L of NL, NL+1 times DL. This is the total number of parameters. All right. Okay. So for a map, let's draw a picture of what this looks like. So you have some input, X. You have a layer, which I'm going to write 1. And this is going to be the L+1th layer, and this is going to be the output y hat. I'm going to write, this is theta 0, 1, 1, and so on, theta 1, and activation functions sigma 0, sorry, sigma 1, and here sigma L+1. And the neuron values in each layer, they're going to be denoted by Z of 1, Z of L, and so on. Okay, so how do you write the mapping for this thing? Y hat of x and theta n. Okay, it's going to be sigma of L plus 1, Z1 of L plus 1 of x and theta n, where the zi's are kind of defined recursively. So the zil plus 1 of L plus 1 over NL to NL of the activation at layer L, the value of the neuron at the previous layer, of x and theta n, and the parameter corresponding to the edge connection between the neurons, right? So to summarize all of this monstrous notation, right? So whenever you see a superscript, it refers to the index of the layer. Whenever you see subscripts, it refers to the index of the weight in each particular layer. You also notice that it's a fairly unusual neural network in that the output of each neuron is multidimensional. It's not as you'd expect from what people call an NLP in practice. But never mind. This is the a bit hard to. Yeah. So never mind. This is the model they're working with, yeah, this is the notation that we need to use. Okay. So I'll draw attention to, I guess, the following first bit of something non-standard, which is this 1 over NL scaling. Okay, which, okay, yeah. Yeah, it's notoriously bad hat to use blue on green, but I don't have red. Oh, there we go. Yeah. Okay. So I'll draw your attention to this scaling, which makes the L plus 1th neuron value look like this empirical average of the neuron values from the previous layer. Okay. So effectively choosing the scaling between the neurons this way will allow us to write down the limiting behavior of the network. Okay. So to look at the dynamics of the weights in time, we need to write down the updates for the weight. So each weight, theta L, at time k plus 1. Again, I'm flying through this because it's reasonably well known. This gradient operator being, and this is where another particularity of this framework comes up. So this is going to be 0 when L is equal to 0 and L. And this is going to be what you would expect. Okay. So this is saying the following thing. For the first and final layer, the weights are being held constant during training. So this is again, a particular type of behavior. And the reason for this, you will see in a second when we write down what this looks like. When you write the backpropagation equations down, you're going to see these NL factors accumulating at a rate of n squared in all other weights, but just at a rate of n in these 0 NL weights. And particularly for this reason, in order to keep the update scales the same for all weights, this assumption is made. But I think that this is possible to lift with a bit of care on how this is done. So just a quick side panel. Okay, so this is starting to look like well, I guess like what you might expect if you've ever seen this kind of mean field framework before. We're starting to put ourselves in a position to take various empirical averages and approximate these empirical averages with population averages over distributions of the weights, right? So the property that that makes this thing possible is something called exchangeability. And it's, again, a fundamental reason why this particular MLP model is used. So we say that a random vector, a finite random vector, is exchangeable if xn is distributed the same as x sigma n for all permutations. Let's not write sigma, let's write tau for all tau in Sn, right? So this is the property that that you see holding for the weights in each layer in the MLP, and this is what will allow us to produce the mean field event. Okay. All right. Instead of erasing, let me just continue here. How should I do? Should I just make a side panel in these boards and continue here, or just start on the new ones? I think just this here is fine. Just so long as it's not confusing going from here to here. But okay, so the thing that you want to write down is you want to write down the backpropagation equations for the evolution of the weights. Again, I'm not gonna do this in detail. But again, it's useful to see how these look like. So if you mercilessly apply the chain rule, this is going to be equal to basically some big average of derivatives of neuron activations. I'm not going to be very precise what the averages are written over. Okay, where these M operators they're going to be defined recursively as this composition of derivatives of the activations in the inputs. Okay, so basically this is the repeated application of the derivative of the activation in every input. It's going to be a sum of these over all of these indices. So J, L plus 2, L plus 1. This is a multi-index, right? So it's JL plus 2, JL plus 3, blah, 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 up to JL plus 1. So it's going to be a big product of these operators. A big sum of these operators multiplied with the L plus 1 multiplied with the theta derivative of every activation. Okay. So what is this huge piece of notation bias? So we want to start thinking about defining these this limit for the large-scale dynamics of the network. The fundamental object, which is our weights in the network, even if they start off independent, and this exchangeability property is satisfied through the evolution in time of the network, it's unlikely that they will remain independent, and it's furthermore even unlikely that they will remain independent in the limit, and I'll show exactly why. Okay. The reason is, and we shall see, that the weights in each layer I satisfy some will satisfy some distribution mu I, mu L, and these mu's will be independent from each other. But the weights in the first layer will never end up decoupling from the weights in the layer before, from the theta zeros. And same thing here, these weights will never end up decoupling from these weights here. So these paths will always stay coupled, simply because there isn't enough in the limit to average over at the beginning and at the end of the network. Okay, so you can see this here, right? This looks like a huge average over forward paths. So this looks like an average over forward paths. Okay, and here this term from its definition, this will be this derivative itself will be an average over backwards paths. Okay, so because all of these weight distributions in the middle layers have a lot of forward paths and a lot of backward paths going both ways, this formulation in the mean field limit will show them decoupling from every other weight in the middle layers. These layers are special in this framework. Okay. All right. So I want to go ahead and state the main results in the paper. And to do this, we've seen that the mean field objects that we're going to be constructing depend a lot on the behavior of weights traveling across paths from the input to the output in the network. So they're going to depend on sequences such as this. Okay. So we better look at these objects as being some sort of fundamental unit of the analysis. Okay, so paths of weights. Okay, so we have for a theta vector from 1I1 in the 0th layer and so on up to the final layer. Okay. This lives in the full parameter space. So this is what we will sort of define as a path of weights. It's capital D. I don't know if you can see, but for any mu in P of RD, we'll write mu I as the marginal over R DI above here. And similar, we're going to write mu IJ for the joint of the two. And for a random variable with distribution mu, we're going to write we're going to write theta I, obviously distributed as mu I, and we're going to write mu of I plus 1, AI plus 1 as the conditional of these two distributions on the event I plus 1 is equal to A. Theta I plus 1 is equal to AI plus 1. This is the condition. Okay. So this is the notation that we're going to use. And we're going to look at extensions of these measures over continuous functions from the interval 0t to r to the d. So we're going to look for measures in here. That makes sense? Maybe one more bracket here. Okay. And we're going to write, we're going to write mu of this interval for the full probability for the full measure, and we're going to write mu t for the time t marginal. Right. So now we're in a position to write down, given the expression for the discrete time dynamics of the network, we're in a position to write down our best guess for what the limiting behavior should be, given let's say our intuition for how these distributions are going to decouple in the limit. Okay. But you'll see it's quite intuitive. It's basically just taking what's above and replacing all summation signs by appropriate integration signs. So I should say, depending on how comfortable you are with this, the kind of hand-wavy way that people explain the mean field limit is that you take empirical averages of you take empirical averages of you take empirical distributions, and in the mean field limit you somehow replace them by a single distribution that the weights follow in that particular layer. I mean, I'm not really comfortable explaining it like this because the whole way you define it kind of depends on the framework that you've set up. But the general intuition behind it is that as the size of the layers go to infinity, and due to this exchangeability property that we have up there, the empirical averages of the weights and basically everything else that happens in these layers tends to the, let's say, the population versions of these weight distributions. Right? So the weights start looking like samples from a particular distribution. Okay, so back to the mean field mean field picture. Okay, so we're going to need to write all of these basically Z values of the neurons, and these are also given recursively. So for x and mu in r to the dx times probability measures on r to the d, right? The mean field activations are going to be some function of x and mu, and they're going to be replaced by these integrals over r d0 plus r d1 sigma 1 sigma 0. Basically the same dependency structure that you see there, except turning the sums into integrals. Okay, left without chalk. Okay, and similar expression for ZL of x mu. One sigma L minus 1 of whatever needs to be here, so Z and A, right? D mu L minus 1 of whatever needs to be here, A L minus 1. Okay, and the final ZL, and this is kind of important, I guess, because this is what creates a lot of the issues in the proofs, is now dependent on the particular value of the weight at time L, at layer L, sorry. This one. X mu, A L minus 1. And here you get this conditional probability appearing. So again, there's no there's no a priori reason why this is the limit. This is still just our guess for what the limit is. Of course, the proofs are going to connect these artifacts to the discrete time dynamics, but this is kind of encoding the dependency structure that we expect, given what we mentioned about how the weights are supposed to decouple in the limit. And the final activation, this is simple. It's again just what you would expect. Sigma L. Sorry, I call these activations, but they're not activations. They're you know, neuron values. Okay. And there is a similar description for these M operators, which is, remember, the M operators were the Z derivatives of the sigma L's. So there's a kind of a similar mean field expression for these parameters in terms of the relevant integrals, which I'm not going to write down. This is something that you can see the source. I could, but I'm afraid that we're running out of time. And by the way, whenever we're working with these mean field objects, the notation has this this bar on top. Hope I didn't forget anywhere else. So we're going to distinguish between the mean field and the discrete objects by this bar notation. And you know, the gradient itself will also have a mean field description in terms of x, y, this mu, and the parameter, and it's going to be, you know, 0 for 0 and L, and it's going to be this y minus y bar x mu plus, not plus, sorry, transpose x mu, which is, this is the sort of the mean field description of the del y y hat. Okay, so again, you can write these down fairly easily, but I'm not gonna go through the exact details. But okay, so luckily this puts us in a position to write our first results down. So okay, so apologies that up until this point it's basically just been notation, but now we can actually discuss the results in the paper. Which one is best to erase, do you think? Maybe the first one, no? Yeah. Okay. Okay. Okay, so the natural assumptions here. Okay, which are that the weights start off independent, both from each other and from the data. So they're IID in layer L, and independent from each other in all layers. Okay, and also independent from the sequence of data points. Okay, and all of these distributions have finite first moments. Furthermore, the output labels are bounded, almost surely, the activations, the alpha, which is, so I forgot to mention, I think, so the alpha was the thing that scaled the gradient dynamics. I don't remember exactly. Oh yeah, here. So the scale of the step size, the derivatives, and the derivative of alpha. These are all bounded, and they're all bounded by the same constant. Okay. So, okay, so we say a measure on path space satisfies the McKean-Vlasov problem for DNNs. If you've seen, if you've seen these kinds of diffusion processes, it'll be a bit confusing, but I'll say a couple of words afterwards. With initial conditions. With initial conditions 0. If there is a variable distributed as mu star, right, such that at the evolution at time t is given by this integral equation. Time 0 minus 0t alpha s, the expectation over xy distributed from the data distribution, and now this mean field gradient operator mu star at time s, theta bar at time s, ds. Okay. So this is their, this is their guess for the dynamics in time of the network evolution under gradient descent. And we can start writing down some results. Yes, of course. Yeah.
So the McKean-Vlasov problem is to find the mean such that this equation satisfies.
Sorry. So we say that this measure satisfies the McKean-Vlasov problem if a random variable distributed as such evolves under an equation like this.
So it's the property of the measure.
It's what? Sorry.
Property of the measure.
Yes. Yeah. I mean, I think we're going to be using it kind of liberally also for the random variable distributed as mu as well. So just through the natural correspondence between a random variable and its law, right? But, all right. Okay. So their first theorem says that this, this problem, this is called the DNN McKean-Vlasov problem. So the DNN McKean-Vlasov problem has a unique solution mu star 0 of t for the equation given above, i.e., there exist unique deterministic functions FL RDL, sorry, small l, into continuous functions. And FL minus 1, L minus 1 cross RDL. You can fill this in such that theta bar 1 of t is the push forward of its version of at time 0. In the two relevant marginals, right? So here, this is a function of t. Okay. And theta L minus 1 t is f of L minus 1, and again, whatever needs to be filled in. So this is the following thing. Is that given any, so obviously, also this is distributed as mu star of 0t. This is required by the definition, right? Okay, so this says that the evolution of the layer-wise marginals decouples as we'd expect. The Lth layer marginal in time evolves as a deterministic function of the initial Lth layer marginal. The 0 and 1 marginals remain coupled, but decoupled from everything else. And here the L minus 1 marginal and the L marginal remain coupled, but decoupled from everything else. Okay. So up until now, this is just a guess for how the limit is supposed to behave in time. And you need to somehow relate it to the discrete dynamics. So again, remember that theta and k was the discrete version of the weights, and we're going to write we're going to write indexes or iteration steps between 0 and this time interval. The second theorem says that kind of at a macro scale, so the loss can be well approximated by the mean field loss dynamics. So we have the expectation over the probability of the data and the initial measure on the weights. So this is the loss on the discrete parameter. This is the population loss on the mean field distribution. This is less than or equal than some constant that depends on all of the other constants that we've put down. So the bounding constant in the assumption, the time, the number of layers, times where D is the max of these neuron input dimensions. Okay, so this is the first thing that tells you that the discrete dynamics couples reasonably to the mean field dynamics that we've defined above, and in fact, even more is true. Okay, so there exists. This is theorem 3. Okay, so there exists an ideal particle which in itself is just a random variable. We'll show how this is constructed. Okay. So there exists an ideal particle which lives in the same space as the parameter. Such that theta bar L is distributed as L 0 t, for L is different from 1 up to L minus 1. Theta bar 1 of I1, I2. So these have obviously the same indices as the discrete particles. This is distributed as mu star of 0 t, the conditional on one of 0 t. Theta L minus 1 L minus 1 IL of 0 t is distributed as the conditional on L. So again, what we expect from before, and we haven't said anything. I'll make an aside here. And the expectation again over the data distribution and the initial distribution of the sum in each layer of the discrete thing, k IL plus 1 minus the ideal thing IL plus 1. I shouldn't call this the discrete thing because this is also discretized now in this equation, is less than k of CTL, the same thing as the other thing there, b over n plus epsilon plus square root of epsilon b. Okay, this is a bit messy, but you get the picture. When I write these constants, they're not always the same constants. Okay, so is it okay if, so it's about 5 minutes till the end. Is it okay if I overrun maybe by 5 to 10 minutes to talk about the proofs and how you argue about these things?
Yeah, well, I'm sure maybe some people would have to go, but I'm here. And
right.
Maybe one room
okay, sure. Yeah. Let me quickly. Okay, so I think sort of at this point, you should kind of have enough intuition for how to do these things yourself. The proofs themselves remain fairly tricky. Okay, but in particular for theorem 1, it follows kind of a standard program. So for the standard McKean-Vlasov SDE, so this is why I said that it's a confusing formulation if you've never seen, if you've seen the McKean-Vlasov SDE before, because it doesn't have a diffusion term. So the typical McKean-Vlasov SDE is something of this type. equal to some drift term dt plus sigma of x bar t. Okay. Where xt is distributed as ft. Okay, so this is the kind of the typical YUKIMURA diffusion. In our case, this term is 0, right? So it's made significantly simpler. On the other hand, because of the conditional dependence because of the dependence of the gradient on the neuron values, and because of the dependence of the neuron values on these conditional probabilities, this won't be Lipschitz continuous. It won't even be continuous in its arguments. So the typical result here is, I don't know exactly who this is due to, maybe Kak or probably McKean. The typical statement about the existence of solutions is that if B and sigma r are kind of uniformly Lipschitz in in both variables, basically. With the W2, the Wasserstein distance between these two distributions, then for any F0, this problem admits a strong solution. Okay. So how are these things typically done, or how is this result typically proved? The trick here, and this is relevant to the problem because this is exactly what they apply, is to kind of construct a fixed point argument. So to define a map from probability distributions on 0t back to itself, okay, which says phi of m is the law of xtm, where xtm satisfies this so now, because this measure is not, this is not required to be the law of XTM, the existence of solutions for this is sort of comes from classical Ito diffusion, and the desire is to find phi has a unique fixed point. To wipe something again. So actually, I probably don't have time to get into detail. So I just wanted to briefly say how you do this for the typical McKean-Vlasov problem. Again, for the typical McKean-Vlasov problem, it's made significantly easier by the fact that you have this Lipschitz condition. It's also made slightly harder by the fact that you have this diffusion term, and you need to kind of. So what you're going to need to find is that phi is a kind of delayed contraction in Wasserstein space. So you're gonna figure out something of this type. I can show you how you get to this point afterwards if anybody's interested. So some constant to the k, some other capital constant of W2 of n and prime with this c here. So you're gonna basically use the Lipschitzianity of the coefficients to bound the Wasserstein distance of the of phi, and use some sort of iterated argument to get an inequality like this for all powers of phi, and this will imply that phi has a unique fixed point. Has a unique fixed point by a simple modification of the classical Banach contraction principle. Okay. Now, the solution to the top problem is much more difficult because of this discontinuity in the drift term in terms of ft. So this this will not be satisfied. But the trick here is to kind of restrict your solution space. So instead of considering all possible measures, consider the measures that actually look like what your solution to the McKean-Vlasov problem should be. So you consider the measures that are push forwards of your initial measure through deterministic Lipschitz functions like the ones that we wrote down on the board. And actually turns out that this set is very well behaved. It's closed with respect to the Wasserstein metric. It's closed with respect to this map here. It turns out that for measures in this set, you do satisfy Lipschitz continuity, and then you once you do all of this work, you can complete this argument. Okay, we're slightly above time. I'm happy to continue giving a couple more details about how you show, well, theorem 1, theorem 2, also this kind of classical result. But I think that it's okay to sort of say this is the main content that we could get through, and it's probably a good time to take a couple of questions if there are any questions. Yeah. I can't see if anybody's typing anything online.
Yeah, but if anyone has questions online, just put it in the answer and the question, or write in the chat and maybe in-person audience. Questions here?
Well, people think I actually have one question, sort of a more general one. This whatever dimension of your layer is.
Yes.
That's because you want a continuous path. Is that correct?
Well, so the fact that something that satisfies this equation will be time continuous, this needs proof.
Yeah, but before that, when you fix the relation, everything, you tell it we want something that is continuously right. Before you came to this equation, you sort of assume that the path that you're interested in should be continuously right. I think that's another word also on a few occasions. Something wasn't continuous function from 0, 1 with values in R.
Yes. Yes. Okay.
So if you wanted more from your part, if you wanted them to be
I see. No, so they will be Lipschitz in time because of, well, I mean, they're defined on a compact interval. So maybe so. So it's a continuous function on 0t,
okay,
right? With values in R to the d, right? It's bounded. So it's Lipschitz. No, so this is not the typical. So I mean, okay. So when in the literature on I guess on machine learning, it's very typical to say something is Lipschitz continuous by specifying I guess by saying that the gradients are Lipschitz bounded or something like that, right? This is what you're talking about.
Yeah, well,
I'm just talking. So I'm just talking about functions like this. This is, yeah, the only.
Yeah. So
yeah.
That's what I mean by Lipschitz.
Okay.
And that's more than just what you.
I'm.
Yeah, we're so exactly. And
so
if you're looking for something that is
so are we talking about functions into probability measures or into measures, or are we talking about just continuous paths from 0 to t into R to the d?
And I think in your framework so far you wanted also say also something that the path to be continuous in time.
No, but
in time. Maybe I'm not making sense. Maybe I'm misunderstood.
So yeah, I think I'm slightly confused.
Maybe I'm.
No. So your question is, if I wanted my paths to be Lipschitz on top of just being continuous,
would it A give me any benefit, and B would it change the result?
so just simply from this definition, you'll be able they will be able to prove that they satisfy a Lipschitz condition. Yes, so it will not give you any benefit with respect to the proofs. Yeah.
Sure, it will not give a benefit. If what you get is Lipschitz anyway.
Right. Yes. So what you get will be Lipschitz anyway. Yes. Mm-hmm.
I don't see anything in the chat either. Want to continue this? At some point we'll have to go to proving them.
Yeah.
Or if you think it's a good place to.
I mean, I think it is a good place to stop. So there's a couple of interesting techniques that have to do with how you, I guess how you prove the second theorem, and yeah, how it would have been a little bit easier if I kind of had time to very quickly work through how you do this fixed point argument in the McKean-Vlasov case, where you see exactly how the Lipschitzianity condition on the drift and diffusion coefficients matter. And then, yeah, I guess the idea was that you use this kind of restriction to a special set of measures to recover these conditions despite your general setting not admitting it. No, I think it's, it's a good place to stop if there are no more questions. Yeah. Okay, no worries. Thank you. Yeah. Yeah. And I'll also photocopy the notes, and the notes have a little bit more, obviously, but I will say that the paper is very self-contained, and I did struggle to use most of the notation that they use in the paper, so you'll be able to kind of match what I wrote to what they did. Yeah.
Thank you.
Okay.
Thank you.
Yeah, no worries.